There is a number sitting in plain sight that mathematics has been staring at for nearly 200 years. It is called Catalan's constant. Its decimal expansion begins 0.915965594177219. We can compute it to any number of digits we like. Hundreds of billions of digits are known. The series that defines it converges in 2 lines of algebra. It shows up everywhere, in physics, in combinatorics, in geometry, in number theory, and yet we cannot prove a single thing about its nature. We do not know if Catalan's constant is rational. We do not know if it is irrational. We do not know if it is transcendental. We do not know if it is algebraic. We have no idea. This is the strange story of a number that lives at the boundary between what mathematics can compute and what mathematics can understand. Today, we are going to look at where Catalan's constant comes from, why it is everywhere, and why proving even the simplest fact about it is, after almost 2 centuries, completely beyond us. Catalan's constant has the cleanest possible definition. Take the sum, from n equals 0 to infinity, of -1 to the n divided by 2n plus 1 squared. Let's compute the first few terms. N equals 0 gives plus 1 over 1 squared, which is plus 1. N equals 1 gives minus 1 over 3 squared, minus 1/9. N equals 2 gives plus 1 over 5 squared, plus 1 over 25. N equals 3 gives minus 1 over 7 squared, minus 1 over 49. If you keep adding these terms, plus 1, minus 1/9, plus 1/25, minus 1/49, plus 1/81, and so on, the partial sums settle down. They oscillate up and down, getting closer and closer to a single fixed value. That value, the limit of those oscillating partial sums, is Catalan's constant. It is named G in most modern textbooks, and the convention is to write it as a capital G with a slightly stylized typeface. The series itself looks almost identical to a famous cousin. Compare Catalan's series to the Leibniz formula for pi over 4. The Leibniz series is 1 minus 1/3 plus 1/5 minus 1/7, with the denominators just 2n plus 1. Catalan's series is 1 minus 1/9 plus 1/25 minus 1/49, with the denominators 2n plus 1 squared. One single exponent, a square, separates the most famous formula for pi from a number we know almost nothing about. Catalan's constant is not just an abstract series. It appears naturally and unbidden all over mathematics. If you integrate the function inverse tangent of x divided by x from 0 to 1, you get exactly Catalan's constant. 2 completely unrelated objects, an alternating series over odd squares, and a continuous area under a curve produce the same number. Catalan's constant is the area under the function negative log of x times 1 over 1 plus x squared, integrated from 0 to 1. It is half of the integral of log cotangent from 0 to pi over 4. It is the value of the Dirichlet beta function at 2, a cousin of the Riemann zeta function evaluated at the integer 2. It appears in lattice statistics, in the spanning tree count for the infinite square lattice, in the Ising model, in the volume of certain hyperbolic three-dimensional manifolds, in the Mahler measure of specific polynomials. Wherever mathematicians look at problems involving inverse tangents, alternating sums of odd squares, or symmetries of the integers and the second power, Catalan's constant tends to appear. It is the natural answer to dozens of questions in fields that have no surface connection to each other. It is, in that sense, fundamental, not as famous as pi or e, but no less universal, and no less mysterious. Now, the question. The single question that has resisted every attempt at answering it for almost 200 years. Is Catalan's constant rational? A rational number is one that can be written as a fraction. 3/7 is rational. 22 over 7 is rational. Even 1,729 over 14 is rational. A rational number, written in decimal, always either terminates like 1/4 equals 0.25, or eventually repeats in a fixed cycle. If you compute Catalan's constant to 100 decimal places, then 1,000, then 1,000,000, the digits look completely random. No repetition pattern emerges. Every test for randomness we apply to those digits Catalan's constant passes. The digits look, statistically, like the digits of pi, like a true random sequence. But looks random is not a proof. The decimal expansion of, say, 1 over 12.23,467,000,000,000 plus 1, that is rational. It just has an extremely long period before it starts repeating. Catalan's constant could be rational with a period larger than any number of decimals we have ever computed. So we don't know if G is rational. And the next deeper question, whether G is transcendental, meaning it cannot satisfy any polynomial equation with integer coefficients, is even more out of reach. We can prove pi is transcendental. We can prove e is transcendental. We can prove e to the power pi is transcendental. For Catalan's constant, nothing. To understand why Catalan's constant is so hard, look at its close cousin. The Riemann zeta function, evaluated at 3, written zeta of 3. This is the sum from n equals 1 to infinity of 1 over n cubed, 1 plus 1 over 8, plus 1 over 27, plus 1 over 64, and so on. Its value is approximately 1.202057. For 200 years, mathematicians could not prove that zeta of 3 was irrational. Every numerical test suggested it should be ma. The decimal looked random, no repeating pattern emerged, but no proof existed. Then in 1978, a French mathematician named Roger Apéry, working largely in isolation, announced a proof. Zeta of 3 is irrational. The proof was so unexpected, so elementary, and so unlike anything anyone had tried, that the mathematical community initially refused to believe it. Henry Cohen and Alfred van der Poorten reconstructed Apéry's argument and confirmed it was correct. It is now called Apéry's theorem. Apéry's method works for zeta of 3. It does not, despite enormous effort, work for Catalan's constant. The constant G is, structurally, what Apéry's machine would need to attack, an alternating series with quadratic denominators. But the specific combinatorial identity that Apéry exploited for zeta of 3 has no known analog for G. We have spent half a century looking for a Catalan version of Apéry's miracle. We have not found it. It is not the case that nothing is known about Catalan's constant. The progress is real, just narrow. In 2014, Tanguy Rivoal and Rivoal-Zudilin proved that at least one of 7 specific Catalan-related constants is irrational. Catalan's constant is one of those 7, so we know that at least one of them is irrational, but we cannot say which. In 2015, Boris Adamczewski and Jan Bugeaud proved that Catalan's constant has irrationality measure at most around 4.2. This means Catalan's constant cannot be approximated unusually well by rationals. Liouville-style transcendence arguments are ruled out. Computationally, billions of digits are known. The current record is hundreds of billions of digits, computed by Alexander Yee and various collaborators using Ramanujan-style hypergeometric series. The digits show no statistical anomaly. There are dozens of efficient series representations. Some converge faster than the original definition. The fastest known formula adds roughly 50 mu accurate digits per term, one of the most efficient rational series in all of mathematics. We can compute Catalan's constant. We cannot say what it is. Why has this resisted us for so long? The honest answer is that proofs of irrationality for specific numbers are almost all ad hoc miracles. There is no general theory that, given a series, tells you whether the limit is rational or transcendental. Each proof, for pi by Lambert, for e by Euler and Hermite, for zeta of 3 by Apéry, is built from a specific combinatorial structure that the number happens to expose. For pi, the structure is the continued fraction expansion of the tangent function. For e, it is the integral representation that makes its partial sums into orthogonal polynomials. For zeta of 3, it is Apéry's accelerated series, which forces a divisibility constraint that a rational value cannot satisfy. Catalan's constant has no analogous structure, or rather, no one has found one. The series for G is innocent. The integral representations are innocent. The connections to lattice models and hyperbolic geometry are deep, but provide no leverage on the irrationality question. This is, in a strange way, an existence question about mathematics itself. Either G is irrational, and there is a proof out there that no one has yet conceived, or G is rational, and its denominator is a specific integer that is hidden somewhere in the structure of mathematics, waiting to be uncovered. Both possibilities are wild. Both possibilities are, today, equally consistent with everything we have ever computed. Catalan's constant is, in a way, a barometer for what mathematics can and cannot do. We can compute the digits of any specific real number to arbitrary precision. We can build powerful series to extract those digits at industrial speed. We can prove deep statistical statements about how those digits are distributed. But the question of whether a specific number is rational, the most elementary question you can ask about a number, is for many natural constants completely beyond us. This pattern repeats. Euler's constant, gamma, the limit of harmonic minus log. We do not know if it is irrational. The Brun constant, the sum of reciprocals of twin primes. We do not even know if there are infinitely many twin primes. Pi to the e, pi plus e, pi times e. For none of these can we prove rationality or irrationality. The picture is the same. The numbers are computable. The numbers are everywhere. The numbers seem random, and the simplest deep question about them is open. Catalan's constant sits at the center of this family. It is not a curiosity. It is a measurement of how much we don't understand. Every digit we compute confirms that the answer, when it comes, will be one of the two possibilities. But until that proof arrives, mathematics holds Catalan's constant the same way it holds prime gaps and the Riemann zeros and the twin primes, as something it can see clearly, count precisely, and not say a thing about. The number is 0.9159655941772219, and counting. We have known it for almost 200 years. We do not yet know what it is.